Have you ever really stopped to think about how a complex idea, something that's just floating around in someone's mind, becomes a real physical thing you can actually hold? I mean, how does a design for a new car engine or a massive skyscraper actually get built? Well, the answer is a kind of universal language, one that translates thought into reality. And that's exactly what we're going to get into. So you start here, right? With a complex idea, a digital model living inside a computer. And you end up with a real, working machine. The bridge between these two worlds, the bit of magic that makes this whole transformation happen, it's a special kind of language. But it's not a language of words. It's a language of precise, unmistakable images. And that language is engineering drawing. You can think of it as the ultimate instruction manual. It has to be so incredibly precise that a part designed in one country can be made in another and it will fit perfectly, down to the tiniest fraction of a millimeter. It's the only way to make sure everyone, from the designer to the person on the factory floor, is working from the exact same page. Now, like any language, this one has its own grammar, its own set of rules. And those rules are what make it so powerful and so universally understood. Without them, it's just a pretty picture, it's art, totally open to interpretation. But with these rules, it becomes a perfect set of instructions, a true blueprint for creation. So the first and probably the most important skill in this language doesn't even involve your hands. It's all in your head. It's called visualization. It's that ability to see an object in your mind's eye, to mentally spin it around, look at it from the top, the bottom, the side, all before you ever draw a single line. Just take a look at these shapes for a second. Real visualization means you're not just seeing flat drawings on a screen. You're actually seeing them as solid 3D objects. Can you picture the hidden corner on the back of that cube? Or what the underside of that cone looks like? That is the skill we're talking about. It's fundamental.
To make sure a drawing from Germany can be perfectly understood in Japan, the language is built on these core ideas. First, you've got graphics theory. That's the geometric backbone of it all. Then you have standards, which are the super strict, non-negotiable rules. Conventions are kind of like industry shorthand, the accepted ways of showing things. And finally, you have the tools, the actual instruments we use to speak this language.
So, let's talk about those tools. How is this language even spoken before computers took over? Well, it was done with this beautiful set of physical instruments. You can think of them as the high-precision pens and paper of the engineering world. And it all starts right here with the drawing board. This is the drafter's canvas. And it's so much more than just a flat surface. See, it has a perfectly straight and smooth working edge that acts as the absolute, unshakable reference point for every single line you draw. Now check this thing out. This is one of the most clever tools in the entire kit, the Mini Drafter. This one single instrument could do the job of a protractor, set squares, and scales all at once. It let a drafter draw perfectly straight lines at any angle and whip out parallel and perpendicular lines with amazing speed and accuracy. A true multi-tool for the drawing board. Of course, for your most common angles, you had the set squares. These are simple, elegant tools used to quickly snap lines at exactly 30, 45, 60, and 90 degrees. By just sliding them and flipping them around, you could build the entire geometric skeleton of a design in no time. And here, this is the heart of the whole toolkit. The instrument box. It was always filled with these beautiful, precision-made tools. You've got the compass for drawing perfect circles and arcs, and the divider, which kind of looks like a compass with no pencil, used for transferring exact measurements from one part of the drawing to another. Even the Hangul pencil becomes a highly specialized instrument here. Picking the right pencil grade is absolutely crucial. You'd use a hard pencil, like a 4H, for really faint construction lines that you could barely even see. Then you'd switch over to a medium HB for the final, bold lines of the object and all the lettering. Using different grades is what gave the drawing its depth and clarity. And the level of detail went even deeper, all the way down to the actual shape of the pencil tip itself. A sharp conical point was great for most things, but if you needed a long, uniform, thick line, a drafter would carefully shape the lead into a chisel edge. They'd even keep a little piece of sandpaper nearby just to keep that point absolutely perfect. It all really boiled down to this one simple idea. The quality of the tools had a direct impact on the quality of the communication. Precision in the instrument led to precision in the final product. It was a real testament to the craftsmanship of the whole field.
Of course, the world has changed a lot.
And while the fundamental principles, the language itself, have stayed the same, the tools we use to speak it have gone through a massive evolution. We've moved from that physical drawing board to the digital screen.
And the contrast is just stark. I mean, we've gone from manual tools to software, from physical paper to digital files. But, the biggest leap isn't just about speed or being able to edit things easily. It's the shift from thinking in flat 2D views to being able to create and play with powerful, intuitive 3D models right there on the screen.
And this brings us to a really fascinating question to think about. We started this whole journey with visualization, that core mental skill. But today, CAD software can render a perfect 3D model for us with just a single click. So as our tools get smarter and smarter and they do more of the visualizing for us, how do we, the creators, make sure we keep that fundamental human skill sharp?